All right, let's dive right into this explainer. Today, we are exploring the truly fascinating taxonomy of the dark. We're going to break down 16 distinct types of black holes. We're literally mapping out the darkness here, going all the way from the observable giants that shape our universe down to the mind-bending theoretical objects sitting at the absolute edge of modern physics. You might picture a black hole as just this one singular cosmic vacuum cleaner, right? But are they all the same? Asking that question actually opens the door to a surprisingly diverse ecosystem. Far from being identical cookie-cutter objects, black holes come in a massive variety of sizes, behaviors, and theoretical frameworks. And just to give you a sense of the extreme scales we're dealing with right out of the gate, consider this. Our very own Milky Way galaxy orbits a monster, Sagittarius A star, that is 4 million times the mass of our sun. Just let that sink in for a second. So, to make sense of this whole shebang, we'll descend through 5 stages, starting off with the galactic heavyweights, then seeing them in action, exploring their mathematical blueprints, taking a plunge into the quantum fringe, and finally, looking beyond the event horizon. Okay, part 1, the galactic heavyweights. Let's size up the observable universe. There are just staggering mass differences between the black holes we can actually observe. We know about stellar mass black holes and, of course, the supermassive giants that anchor almost every large galaxy. But the real breakthrough lately is right in the middle, intermediate black holes. These were long thought to be basically mythological, but recent observations confirm they absolutely exist in dense star clusters. They might actually be the missing link seeds that eventually grow into those supermassive monsters. Now, stellar black holes are by far the most common type out there, but really think about the extreme compression going on here. The core collapse of a massive dying star packs up to 20 times the mass of our sun into an invisible footprint that is smaller than your average city. It's just wild. Moving right along to part 2, black holes in action, going from silent lurkers to absolute feeding frenzies. There is such an intense contrast in how these objects actually behave in the wild. Astronomers estimate there could be up to 1 billion quiescent black holes just drifting silently in our galaxy. They're totally invisible because they aren't eating anything at the moment. But man, when a supermassive black hole feeds, it turns into an active galactic nucleus, or AGN. The material falling into it forms this superheated accretion disk that can shoot out plasma jets at nearly the speed of light. It creates quasars that literally outshine the entire rest of their host galaxy combined. So, since those quiescent black holes are totally dark, you might be wondering how we ever actually find them. Well, astronomers have to rely on some pretty clever observational tricks, like gravitational microlensing. Basically, they have to wait for a black hole to drift exactly in front of a distant star, which temporarily magnifies its light. It's like finding a microscopic needle in a cosmic haystack, which is exactly why the very first confirmed detection of an isolated stellar black hole using this method only just happened in 2022. Now, what happens when 2 of these dark objects actually meet to form a binary system? Well, their inward spiral radiates massive ripples in the fabric of space-time itself. And when they finally merge, they release more energy in a fraction of a second than all the stars in the visible universe combined. No joke. Yet it's entirely invisible to traditional telescopes. We only know what happens because we finally detected those space-time tremors at the LIGO Observatory back in 2015. All right, part 3. The mathematical blueprints. Let's strip away the space dust and look at the elegant code of the cosmos. There's this brilliantly elegant concept called the no-hair theorem. It proves that black holes are actually incredibly simple objects at their core. Once something falls in, all of its complex details are just lost forever. Mathematically, a black hole can be entirely described by just 3 specific numbers: its mass, its spin, and its charge. The Schwarzschild model is the absolute simplest, dealing only with mass, while the Kerr-Newman model combines all 3, giving us the most complete mathematical description we have in classical general relativity. Looking at that simplest model, the non-rotating Schwarzschild black hole, it actually gives us the mathematical formula for the fundamental size of an event horizon, which we call the Schwarzschild radius. And this leads to some truly mind-boggling thought experiments. Imagine taking the entire mass of the Earth, every mountain, every ocean, and crushing it down so incredibly small that you could put it in your pocket. It would be smaller than a marble. But here's the catch. In reality, almost all black holes are spinning, making them Kerr black holes. Because they spin, they create this incredible phenomenon called frame dragging, literally pulling the very fabric of space-time around with them like a whirlpool. This creates a terrifying, inescapable zone just outside the event horizon called the ergosphere. Physicists theorize that the rotational energy in this ergosphere could actually be tapped as an enormous cosmic power source through something known as the Penrose process. Which brings us nicely to part 4, the quantum fringe. This is where classical physics basically shatters. First up on the fringes are primordial black holes. These guys offer a totally different origin story. If they exist, they weren't born from dying stars at all. Instead, they'd have formed from the intense, compressed heat of the early universe, just fractions of a second after the Big Bang. Some physicists believe the universe was so insanely compressed back then that random pockets of space just collapsed. They could be microscopic, or they could be enormous, silently floating through the universe completely undetected. And speaking of microscopic, we have to talk about microblack holes and Hawking radiation. Stephen Hawking famously predicted that black holes aren't actually entirely black. They slowly leak energy over time. By the way, this leakage perfectly explains why the public panic years ago over the Large Hadron Collider creating subatomic microblack holes was completely unfounded. Even if those extreme particle collisions compress space enough to make a subatomic black hole, Hawking radiation dictates it would evaporate in a literal fraction of a second. No doomsday here. Then we've got the ultimate rule breaker, the naked singularity. In a normal black hole, the singularity, that point of infinite density, is safely hidden away behind the event horizon. But mathematically speaking, under extreme conditions, that horizon could actually disappear. This concept completely breaks the rules of physics, which prompted Roger Penrose to propose the cosmic censorship conjecture. He essentially argued, no way, nature simply does not allow this, and that the universe will always step in to hide its singularities. Now, if we zoom all the way down to the absolute smallest scale imaginable, the Planck scale, things get seriously weird. At these incredibly tiny limits, gravity becomes as strong as the other fundamental forces. A black hole here would weigh about 22 micrograms, which is actually massive for a subatomic object. This represents the absolute bleeding-edge frontier of what physics can currently describe. To really make sense of it, we'd need a complete theory of quantum gravity, which, spoiler alert, we simply don't have yet. Finally, part 5, beyond the event horizon, it is time to tackle the ultimate existential questions. As physicists desperately hunt for that unifying theory of quantum gravity, string theory throws out a wildly bizarre alternative, the fuzzball. This controversial proposal attempts to solve a genuine crisis in physics by completely replacing the event horizon and the singularity. Instead, you get an incredibly dense, solid tangle of vibrating strings. From the outside, it would look exactly like a black hole, but inside, that terrifying infinity of a singularity is replaced by a massive, fuzzy knot of foundational strings. And that brings us face to face with the massive crisis that theories like the fuzzball are trying to solve. If Hawking radiation slowly evaporates a black hole over incomprehensible timescales until nothing but a tiny remnant is left, what happens to all the stuff that fell inside? This is the terrifying black hole information paradox. Quantum mechanics rigidly says information cannot be permanently destroyed. So when the black hole finally vanishes, does the information come back out, or is it gone forever? I am going to leave you with that profound thought to chew on. Black holes aren't just heavy objects floating in space. They are the ultimate stress test for our physical laws. If information truly is permanently destroyed when a black hole evaporates, answering this question might require us to rewrite everything we think we know about the universe at its most fundamental level. Thanks for joining me on this explainer, and keep questioning the dark.